Hi, I am Shola Wylie, and this summer I studied granular impact dynamics, especially, to be exact, the effect of the intruder shape with impact dynamics. So what are granular materials? Granular materials are large-scale collections of discrete macroscopic particles. This can be sand, pills, cereal, or asteroids, or even traffic. Collective behavior of granular materials can resemble solids, liquids, and gases, but strange solids and liquids and gases because the thermal energy does not move or affect granular material, but external forces do. So this means that ordinary thermodynamic laws don't apply to granular materials because the KT term, the thermal energy, is much smaller than the MGD term, the gravitational potential energy. This causes a very different behavior than normal fluids, solids, or gases. So an example of this is a can of nuts. When you shake a can of nuts, and there's different size nuts, the larger nuts tend to go to the top, which is kind of counterintuitive. You would expect all the nuts to mix and be distributed all over the place. But now they're getting segregated, which seems to go against the law of entropy. The entropy should increase. But because KT is much smaller than MGD, and it's effectively zero in this case, the ordinary laws of thermodynamics don't apply. So, so what I studied, especially this summer, is granular impacts. And when a force is applied to a solid or liquid, like a normal solid or liquid, it's distributed uniformly through the material. So when you press on a solid, it gets distributed throughout the solid evenly. When a force is applied to a granular material, though, it propagates through the material on curved particle chains called force chains. You can see in the picture to the side with the 4 square boxes that all those little lines, you have an intruder coming in, and all those little lines are force chains, and the spaces in between the lines don't even feel the force of the intruder. It's just on those force chains. And you can see in the bottom corner a bunch of blue circles, and those are representing grains, and the arrows represent forces. So if we have a force coming down the first grain, it might go affect the particle to its side, to one of its sides, but not the other, and create a force chain along that. But all the other particles are not affected. So it's strange, but only some particles feel the force, while others won't, which is not the case in liquids or solids usually. So when an intruder impacts a granular material, the force chains exert resistive force to decelerate the intruder. So when you drop a ball into sand, the ball is going to stop at some depth because the granular material is exerting a force that resists it. So a typical scaling law for spherical particle interactions, spherical intruder/particle interactions, is D is proportional to AH to the 1/3. A is just some constant, but D is the depth beneath the grains that the intruder goes, and H is the depth beneath the grain the intruder goes, plus the height, or the height above the grains that the intruder is dropped. So it's the total drop height. And you can see that in the picture to the side. So basically my objective this summer was to examine how the scaling law, motion of the intruder, and motion of the particles change with intruder shape. And below you can see all the intruders I used. I used 7 intruders with they were cylinders with cones at the end that varied in angle, and I labeled them by the different angles, how pointy they were generally. So here's a video of one of the intruders I used impacting the grains I used. Let's play it. Here, and you can see all the particles move and the intruder go in, and it's very clear. And here's another one. Here's the greatest angled one, the most pointy one. And again, you can see all the particles move. But in order to do this, when we do this, we have a glass box that we're dropping our intruders in, and we don't want to just see the outer layer of the grains. We want to see within the box, in the plane that the intruder is falling in. So we have to use this technique called refractive index matching. So here in this video, we have a bunch of water beads, and we have water, and we will pour the water into the water beads, and the index refraction of the water beads will match the water, because they're both water, and it will look clear. You will no longer see the beads. It'll look see-through, like it's all one liquid. So we pour the liquid into the beads, and they become clear. Those are bubbles in there that you see, but it should be, we would just stir it and it should be completely clear. And this is, the purpose of this technique is to look inside the grains. So the experimental setup is basically we have this glass box with glass beads inside, and we pour this chemical DMSO and water into the beads, and DMSO and water have a very close index of refraction to glass. So when we pour it in, the beads disappear. It looks like all one fluid. You don't see any beads, just like in the previous video where we poured the water into the water beads. So then after we do that, when it looks clear, it looks like one fluid, you can see straight through it, we add this dye that fluoresces under 66 nanometer light, which is red light, and we shine two lasers on either side that create a laser sheet. So it's just a plane within the liquid, and this plane of light fluoresces the liquid in that plane, but not the beads in that plane. So you can see this cross section of the beads. You can see this cross section of the fluid and beads. So you see dark circles for the beads and light for the fluid, and nothing else. None of the other beads in the box show up because they're not in the plane, and it's see-through except for that plane because the liquid is fluorescing. And we capture all of this with a high-speed camera. And we did drop heights of 2 centimeters, 7 centimeters, and 20 centimeters. For the 2 centimeters, we took videos of all the intruders falling into the particles, so 1 through 7 intruders. And we particle tracked we used a Crocker-Greer algorithm to particle track all the particles and find their paths. And in this picture, and you can see all the paths of the particles, and as the particles change from red to blue, that's as time is increasing. So per each time frame, it gets the particle gets a bit more blue, and so it goes red, purple, blue, pretty much. And then we measured the angle that they go off from the horizontal, and we took it as symmetric around the center axis of the intruder, so both sides we took a symmetric. And we measured this angle, and we wanted to find like where the particles, what angles they tended to go off at. So you can see in this graph to the side that they tended to go off for this particular one between 150 and 120 degrees, a little bit of deviation from that, but not much below 90 degrees. So they all tended to go up in that general direction. So we did this for all the shapes for 2 centimeter drop heights, and we graphed their probability density of the grains against the direction of the grains. And you can see that they tend to stay around, they tend to peak around around the 3 pi over 4 area, or angle, sorry. But you can also see that as the shape as the intruder becomes more angled, it tends to move towards pi, like the peak tends to move towards pi. But for all intruders, the particles are most likely to move between 120 and 150 degree range rather than radially outward. So for that scaling law that I showed you in the beginning of the presentation, D is proportional to AH to the 1/3. I wanted to see if that was the same for these non-spherical shapes. So the way I did that was I took a log-log plot of the depth versus the total drop height, the total drop height versus the depth. And in this graph or plot, the slope of the lines gives the exponent, the small a, in the equation to the above corner. And the dotted line is the 1/3 spherical predicted scaling law, the one for the spherical intruders. And you can see that that slope doesn't match any of the other slopes. All the other slopes of all the other intruders, the non-spherical ones, are not equal to 1/3. In fact, they're all smaller. And the slopes tend to decrease as the intruder becomes more angled or pointy. So we can see that the scaling exponents of all 7 intruders were not 1/3, and the common exponent of this a spherical particle impact, and that the shape of the intruder does influence the final depth, and therefore the scaling law needs to be modified for the non-spherical shapes. We also see that the intruders with the greater slant angles, i.e. the more angled, reach greater final depths. Future work, we want to examine how the shape effects affect the rotation/tilting of the intruder. We observed that a lot of intruders with greater slant angles, i.e. more angled, tilted and rotated more. We also observed that intruders dropped at higher drop heights, tilted and rotated more. We also want to examine how tilting/rotation affects particle scale rearrangements. So we would like to take videos and particle track ones where the intruders tend to tilt a lot. And we also want to examine particle scale rearrangement for higher drop heights. We only did for 2 centimeter drop heights. And I'm just going to leave you with a final video that shows the tilting that we observed. So when we say tilting, we mean that it falls straight in the intruder, but when it reaches the grains, it starts to tilt. So it's not like we were, but basically it tilts when it hits the sand, not before it hits the sand. And acknowledgements, we would like to thank the Lathrop Lab for letting us borrow their camera, and also this work was supported by Trend Training and Research Experience in Nonlinear Dynamics, which receives its support from the National Science Foundation. Thank you.